Hello everyone, welcome to our video presentation for MAT438, Foundation of Applied Mathematics. Today our group will take you through a detailed step-by-step solution for the 4 distinct integrations techniques assigned in set 2. Let's dive straight into question 1, which requires integrations by part.
For part A, we are evaluating integrate x to the power of 5 ln x to the power of 4 dx. First, we simplify using logarithm properties to bring the exponent out, getting 4 integrate x to the power of 5 ln x dx. Applying the LIATE rule, we assign u as ln x and dv as x to the power of 5 dx. This gives us du equal to 1 over x dx and v equal to x to the power of 6 divided by 6. Plugging this into the integration by part formula and distributing our constant, our definitive final answer yield 2 over 3x to the power of 6 ln x minus 1 over 9x to the power of 6 plus c. Let's move to part B, which is a definite integral. The definite integral from 0 to 3 of the quantity 3x squared minus x times cosine of the quantity 1 minus x dex. Because the polynomial factor 3x squared minus x terminates upon multiple derivations, we can use the highly efficient tabular integration method. Be extremely careful here with the chain rule when integrating cos 1 minus x, which introduces alternating sign. After completing the table, our algebraic antiderivative function out to minus 3x squared minus x, sin 1 minus x plus 6x minus 1, cos 1 minus x plus 6 sin 1 minus x. Evaluating upper limit 3 and lower limit 0 with absolute precision leads us directly to the final exact evaluation of 18 sin 2 plus 17 cos 2 plus cos 1 minus 6 sin 1.
Now, let's look at question 2, which requires us to integrate cos 2x over 4 plus sin squared 2x dx using the substitution method. Looking at the integrate, we can see that the derivative of a sine function relates to a cosine function. Thus, we select u equals sin 2x. Differentiation both sides give du equal to cos 2x dx, meaning our numerator component cos 2x dx can be substituted with 1 over 2 du. This transforms our original expression into the clean standard form of 1 over 2 integrate 1 over 4 plus u squared du. We instantly recognize this as the classic inverse tangent integration archetype where a equal to. This integrates smoothly to 1 over 4 arctan u over 2 plus c. Substitute back our original u, our final result is 1 over 4 arctan sin 2x over 2 plus c.
Moving on to question 3, we evaluate the integral of 6x divided by x squared minus 9 to the power 3 over 2 dx via trigonometric substitution using x equals to 3 secant theta. First, we find the differential element dx equals to 3 secant theta tangent theta d theta. Next, we substitute this expression back into our root structure using the fundamental identity secant squared theta minus 1 equals to tangent squared theta. Our denominator reduced from 9 tangent squared theta to the power 3 over 2 to 27 tangent cube theta. When we simplify the full integral expression, it collapses cleanly down to 2 times the integral cosecant squared theta d theta, which has a non-standard integral of negative 2 cot theta plus c. To return to our initial variable x, we refer directly to the reference triangle on the slide. Because secant theta equals to x over 3, the cotangent of our angle is adjacent over opposite, giving us 3 over square root x squared minus 9. Multiplying by our constant scalar gives the final result is negative 6 over square root x squared minus 9 plus c.
Let's address question 4. We are asked to evaluate the integral of 4x plus 1 divided by the quantity x plus 1 squared times the quantity x squared plus 4 dx. Because we have a repeated linear factor and irreducible quadratic factor in the denominator, we must use partial fractions decompositions. We set up our decomposition as capital A over x plus 1, capital P over the quantity x plus 1 squared, and quantity Cx plus D over x squared plus 4. To find our unknown constant, we must multiply both sides by the common denominator to get our basic equation, which is 4x plus 1 equals to A times x plus 1 times x squared plus 4 plus B times x squared plus 4 plus Cx plus D times x plus 1 squared. Instead of expanding, we can solve for our variables efficiency by substituting strategic values for x. First, we let x equals negative 1. This eliminated terms containing a, c, and d, simplifying down to negative 3 equals 5b. This gives us our first constant, b equals negative 35. So we systematically substitute our values of x to create a manageable system of equations. By setting x equals to 0 and plugging in our values for b, we get the equation a 4a plus d equals 75. Setting x equals to 1 yield the equation 10a plus 4c plus 4d equals to 8. And setting x equals to 2 give us 24a plus 18c plus 9d equals to 69 feet. Solving the system of linear equation simulations give us our remaining constant. A equals to 14/25, c equals to negative 14/25, and d equals to 29/25. Now that we have all our constant, we will write our singularity integrate into separate, manageable fractions and integrate them terms by terms. For our first terms, 14/25 times the integral of 1 over x plus 1 integrates easily to 14/25 natural ln the absolute value of x plus 1. For our remaining terms, we split the quadratic numerator, integrating negative 14/25 x over x squared plus 4 using u substitution give us negative 7/25 ln of the quantity x squared plus 4. Finally, 29/25 over x squared plus 4 fits the standard inverse tangent form, which integrates the 29/15 arch tan of x over 2. So all this, we combine all these p's together. Our absolute final is 14/25 ln x plus 1 plus 3/5 times x plus 1 minus 7/25 ln x squared plus 4 plus 29/15 inverse tangent x over 2 plus c.
I just had to let you know you're